My name is Anissa Mitchell, and I'm with PMD Alliance, and I'm excited to invite you today to our program on how exercises increase brain adaptability. This is part of our Proactive Brain Health Alliance program. So we started the Proactive Brain Health Alliance initiative last summer. So we've been doing these educational programs geared towards those who are very interested in learning the causes of neurodegenerative disease and how they can pursue brain health. So what types of education we can give them, what ways they can get involved in their community, what kind of action can they take. So we created this program to give you some specific topics for those who may not yet be diagnosed with anything. They might be at risk. They might be experiencing prodromal symptoms. But even if you are, everybody's very interested in maintaining brain health and slowing any kind of impact that they can through a variety of different ways. And so the focus of these programs is to kind of give you some actionable items. And today the actionable item is exercise, and we're going to be delving into that. We also have a quarterly program that brings people that are prodromal together and gives them an opportunity to meet with one another, to ask questions of an expert. And so we'll be doing that in June. But if you go to the Proactive Brain Health Alliance website, we do have our own webpage. You can look at all of the recordings. This will be added to the recordings, and you can go back and review if you've not seen any of those yet. Excuse me. Some of the other programs we've done on genetics and environmental exposure and REM sleep behavior disorder, those kind of topics. So we invite you to do that, and we will drop the website in the chat. And I think actually Kelly has, so thank you, Kelly. I will also let you know that as we're hearing from our speaker today, if you want to drop your questions in the chat, we'll be reviewing those at the end. And then before we end the program today, we're going to have two really quick poll questions. We just like to get feedback from you all as to whether you got some new information and if this has been helpful. So we'll prompt you at those points. So I want to introduce our speaker today. So we're excited to have Dr. Giselle Petzinger. She is Associate Professor of Neurology at the Keck School of Medicine of the University of Southern California, Los Angeles. She's a board-certified neurologist specializing in the care of people with Parkinson's, and she divides her time between clinical care and laboratory research. Her primary focus and research is to better understand how to promote brain repair following injury and to translate those findings into new therapeutic treatments. Dr. Petzinger has been involved in numerous federally funded research grants and is currently a principal investigator on the U.S. Army research grant entitled Behavioral and Pharmacological Enhancement of Neuroplasticity in Basal Ganglia of the MPTP lesioned mouse and non-human primate. That's a mouthful. Yes. And if you don't understand what that is, I'm sure she's probably going to explain a little bit about that today. But I'm going to welcome you, Dr. Petzinger, and I'm going to hand this over to you.
Awesome. Well, thank you. And I see we have people from all over, which is great. Let's go ahead and get started. I'm going to share. I will, again, give some detail, but also kind of summarize into big picture so we know kind of where we're headed. So with that said, again, just to, introduce myself, Giselle Petzinger. I'm a movement disorder specialist. I've been in the field for a while, and again, call home in Southern California. What we're going to talk about today is Parkinson's disease, but more importantly, everyone's, of course, interested in exercise. I'm interested in exercise. But really, at the end of the day, I'm interested in figuring out how the brain works, no big deal. Just trying to figure out how do we drive brain function? How do we optimize brain function? And it turns out Parkinson's is a great way to study that. I'm just showing you some pictures here, and it's just, I'm not even going to run that slide. I'm just showing you, this is kind of a traditional thinking about Parkinson's. You see a brain there, it's cut, sliced, so you can see kind of the below in black are these square figures that show you what we call the substantia nigra. It's actually dark. It's dark for a reason. It has melanin. So it's dark and those are cells. And what you can see between the left and the right black squares is, on one hand, you can see a lot of these dark cells. On the other hand, on the right, there's less. And what it's telling you is that there's less dopamine producing cells in the brain of Parkinson's disease. It's not that it's all gone, but it's definitely decreased. What I'm also trying to show you in the arrows there is that, when we talk about the brain, we're not talking about really just cells. We're talking about connections. And if anybody, works on cars or, likes to put wires together, I don't know if people like to do that anymore, but the point is, that's how I think about the brain. It's really about connections. And behavior, everything we think about behavior really isn't a cell thing. It's not individual cells. It's about how cells are connecting up with other cells. And I'll explain that a little bit. But this is just sort of a big picture. Oh, yes, here's where the changes are in Parkinson's disease. And these changes are explaining, motor, which is, physical mobility. And those physical mobilities we tend to think about is slowness, stiffness, balance, and in general walking difficulties. Now, you and I know that if you've learned anything about Parkinson's disease, it's a little bit more complex than that. We're going to talk a little bit about thinking, which is what I really enjoy talking about because, well, it's important for pretty much everything, including movement. So let's go and talk about, pardon me, these things are taken off. This is a circuit. Now, I love this, right? It's crazy how complicated this can be. But what I'm trying to show you here in another picture is what's called, the hemispheres of the brain. And what you're seeing is if the eyeball would be up here where I'm pointing, and then this is the back brain down here. Obviously, I'm showing you in colors, just some examples of connections across the brain. And that's what I study. I study these connections. And why do I study them? Because that is what influences behavior. These connections influence my ability to move and my ability to think. And when we think about Parkinson's, like I said, I showed you that first figure. Oh, yeah, it's dopamine cell changes, right? We saw some changes in cells. The dark cells were fewer. But the truth is, Parkinson's disease it's thought of as dopamine cells changes, but the truth is it affects every part of this circuit. And that's not too surprising because, as I said before, really the brain functions by connecting up with other cells. So when we look at Parkinson's, we actually think about it at a circuit basis. And I'm just going to point out a couple kind of key areas. Here's the front part of the brain called the frontal cortex, not too surprising for its name. And that's where we think, this is where our planning processing occurs. In the middle is the basal ganglia. This is where the dopamine cells that I was showing you, they're dropping dopamine in there. And the back of the brain is called the cerebellum. That's important for coordination. We're going to talk about all three areas when we talk about exercise. Okay, one of the first things I wanted to talk about, though, really quickly, is I'm going to talk about this guy back here. The reason I want to talk about him is because he's under talked about. He's kind of ignored. And he's kind of sad about that. I'm sad about that because the bottom line is it actually is important, doesn't get a lot of credit when we talk about changes in the brain with Parkinson's. But this cerebellum, and I'm going to highlight it a little bit more toward the end, if anybody's had a little bit too much to drink and they start wobbling around, well, that's your cerebellum telling you that it's not happy because alcohol affects that part of the brain. But more importantly, what it also tells you is the cerebellum is very important for coordination. And if we know anything about movement, coordination is pretty damn important. And it does get affected in Parkinson's disease. I'm highlighting that because I want you to remember something. I want you to remember that cerebellum. When we start talking about exercise, we're going to go back and talk about some effects on exercise there. And then finally, I want to actually move to the right here before I do anything. And all I want to show you is, this is an example of a cell right here. This is a normal cell. And yeah, you can't see that under a microscope without a very high, very sophisticated microscope. And we certainly don't see that on a brain MRI, right? I mean, I can't see that, right? This is using a high-end microscope to see those cells, and we actually fill it with dye. But what I want to show you is when we blow up one of these connections of these cells, look down below, what you're seeing are these little thorn things, right? Well, what those are actually connections. Isn't that cool? We can actually see that. And what I want to point out is when we have dopamine depletion of the brain, I want to show you what happens to these connections. You see that? Lots of connections, lots of thorns, less connections, less thorns. Does that make sense? Why am I telling you this? Because I don't think it gets emphasized enough that really, again, at the end of the day, right? Connections is everything. Connections is how behaviors occur, both thinking and movement, but loss of connections is what creates the clinical features of Parkinson's. It's not from a cell change, it's from connection changes, all right? remember that because we're going to tie that back into exercise. Pardon me, bear with me one more time. Remember I told you the cerebellar, right? Okay. I just want to show you how important this is in Parkinson's disease. And again, it doesn't get highlighted enough. See this little guy in the back? He's got a little red dot around it. This is a cerebellum again, another way of looking at it. And yet another way head on in the middle. And this is coming from the front of the brain. So I'm just showing you here in blue. These are patients with Parkinson's that are doing activities like using their hands or learning to do some tapping experiments. Although my point is that in Parkinson's, it's super activated. And that's why I think it's really cool. And I'm bringing it up because, well, like I said, we tend to think about dopamine cell changes. We tend to think about the basal ganglia, cerebellum, not so much. So we're going to bring that up again. Okay. Big picture, 5 yards back. Let's start from big picture. Why do we care about exercise? Why do we care about anything regarding experience to begin with, right? So experience is things that you're doing, right? That you're experiencing. And obviously exercise is a big part of it that drives plasticity, right? It drives change. And we know that, right? We know this in kids. We certainly know that this is how children learn to move, right? They learn to walk. They're doing things on a regular basis with multiple practices. If you want to read a book about that, read Malcolm Gladwell, Tipping Point, which tells us not only that experience is important, but practice. And so really, at the end of the day, if you really want to change your brain, you're going to have to invest some time. I mean, that's the bottom line here, right? The brain does change. That's called neuroplasticity, but it doesn't do it by dripping things in our brain. If anybody's seen The Matrix, which I have, of course, that doesn't happen, but you know that, right? So there isn't going to be a computer chip that's going to make that happen. The bottom line is there's a reason we need to go through experience. We need to do things in order for our brain to change, okay? The newest thing, though, and maybe not so new, this was Decade of the Brain. If you look to the far right, who do we have there? Well, we have older individuals like myself. And the cool thing about this, which we don't emphasize enough, is that affective experience on the brain, whatever you call that, we're going to talk about exercise, but whatever that is, right? It's always affecting us, you see. It doesn't matter what your age is. And for that matter, it doesn't even matter what disease you have, right? The brain doesn't care. It's built for that. So it doesn't suddenly change because you get older. It may be different, but it's capable. That brain's sole function is to respond to experience. That's the key. And it never, ever goes away. So when people started looking at the idea of exercise in particular, and you'll hear the term physical activity or exercise for the purposes of this talk, we'll call it the same thing. People started looking at it predominantly for lowering risk of different diseases. And you could pretty much add, Parkinson's and exercise, Alzheimer's and exercise. I mean, I could go on and on here, right? And the bottom line is that exercise is good at reducing risk for many diseases of the brain. It doesn't mean that it stops it, right? It doesn't mean that, every athlete on this planet should never have any illness, all right? That's nonsense. What it does mean is it gives you a lower chance of getting it, right? And I would argue, as we're talking about it in the concept of people, in the context of people who have it, it can also counterbalance changes that are happening. What I mean by that is exercise and experience is always going to be your counterbalance for any type of injury you have. It is always going to be on the side of good, let's say. It's on the side of wanting to make connections, of wanting to make the brain hardier, regardless of what that injury is, right? So if you think about the injury on one side, the bad guy, right? And you think about exercise on the other side, right? You can imagine sort of this balance, right? And that balance exists throughout our life, right? We don't live in bubbles, right? I don't isolate myself from every pollutant that's out there, right? Maybe if I lived in space or not. The point is that this is something that is part of our lives. And so whether it's Parkinson's or anything else, right? Exercise is always relevant. And as I pointed out, these studies said, okay, it may reduce my risk from getting a disease, but my argument is that is always going to be the truth. It's always helping me, whether it's reducing my risk, but also helping me in the context of disease. Okay, so that's a big point. And I that may come up again at the end, but I think we don't want to lose the forest through the trees here. Big picture exercise is good. And this is not surprising. I've told you what the brain wants to do. It's kind of like a duh, right? Yeah. Okay. So now look at all these wonderful things that you can do. Now, I'm not going to talk about any of these specific things. And why? Because the brain doesn't know that. I don't know. You think the brain goes, oh, now it's tango. No, it doesn't. Of course it doesn't. All it cares about is experience. Now, how you want to get there, knock yourself out. It doesn't matter. I think the key, though, and I'll give over some really key points about this that underlie all this stuff, have a good time. Enjoy what you do. And guess what? If you pick what you enjoy doing, surprise, surprise, you're going to get more out of it. I mean, anybody taking a class that they've regretted they're sitting in and they're literally sitting there in pain, not learning anything, wanting to walk out, you follow me? So it matters that you find meaning and it's enjoyable, right? Forcing someone to do stuff isn't going to make, a hill of beans if you're not engaged in it. So that's really important. Now we know currently that there's a lot of benefits from exercise, and that I'm going to kind of set that aside for a bit because we're going to kind of, as I said, I want to get some big picture ideas of what we're learning and importantly, some take home points. So what's the point of this slide? It doesn't really matter what you do, but you should be doing something that you enjoy doing. So, okay, I promised you some parameters. Oh, before I show you parameters, I'm just going to show you some pictures. These are just examples, no change in med. And I get asked this all the time. It's like, yeah, stop. This is exercise. And, people were always shocked, like, yeah, that can't happen. It's, yeah, I can. But is this surprising? Is it surprising based on what I told you, right? You think that person got better from May to August? That wasn't an overnight thing, right? That's investment. So if you want to make a brain change, right, it's an investment, right? You have to sweat, but we know that. We know that about learning a language. We know that about anything, right? There's an investment and you need to practice, right, to get that investment back. And this is just another example of that. The other thing I want to point out is, dopamine is it's a great drug, right? L-Dopa, which is going to become dopamine, is great. It's an enhancer. It helps. It helps with once connections are made, it's like super glue. It helps those connections stay in place, right? But at the end of the day, it's not going to make a person go from what that individual looks like on the left to the right. That's not dopamine, okay? That is practice. That is practice on dopamine, okay? So dopamine is 50% of the story, 50%. It's an enabler, but it does not take the place of practice. And I think you're getting that point. I can't emphasize it enough. It's an investment, right? If you really want to make a brain change, you've got to invest in it. Okay. So another nice picture before we go into specifics. Well, when my husband and I started taking a look at this, and we were looking at it very early, we are one of the first groups to show this in Parkinson's, and we were actually one of the first groups to talk about neuroplasticity when people didn't believe it could happen. And now that seems pretty silly, as you can see. But this is an old paper from 2013, as you can see. And we were very interested in understanding exercise from two components because, well, there's different ways you can study it. I mean, you pick up any paper, it's going to tell you something very different. What I want to point out, though, is we are aligning with the point I just made when you look to the left. I'm talking about brain change plasticity. I'm talking about connections. What's the other name for it? It's synapses. So a lot of what we're going to focus when we think about exercise and the benefits is going to be heavy on the left side of this story. Synapses, connections. That's what I'm all about. I'm an engineer, you see. I want to fix this brain. And if I want to fix that brain, I'm going to have to get into these circuits. There's no way around it. And I've got to understand fundamentally what causes these connections to break and how do I fix them? And more importantly, where in the brain should I be looking? To the right are other types of study people do in exercise. And you've seen them yourself. Trophic factors, what happens, from blood, what's coming in from the blood, whether it's, glucose, whether it's trophic factors, whether it's the immune system, blah, 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 blah. I could go on, but I won't because I care about the left. Okay, so we're focusing on the left. Boom. Okay, so what is plasticity? Well, let's go through this. Big concept. Simple. It's reorganizing your brain. And remember, if we're talking about reorganizing your brain, where are we going to do it? In circuits. If you haven't got that by now, you need to start writing that down. It's connections and circuits. So plasticity fundamentally is making those circuits stronger connecting better, right? You can even argue maybe sometimes in the case of injury like Parkinson's disease, maybe one part of the circuit takes over another part of the circuit, right? It's pretty cool, I'm telling you, what can happen when you're talking about plasticity, because it's not just about connections, but it can also mean that one connection is getting better than the other. I think the other thing, here's a new term. How about this? Brain's attempt to reach and maintain homeostasis. So what is homeostasis? It's a new normal. It's a new balance, right? It's a new way that the brain is connecting up. Now, that process, right? If I want to make a change in this connection, if I want to drive a change in that connection, right? I'm going to tell you that takes a hell of a lot of work, like a hell of a lot of work. You can't just sit there on your couch or chair and wish it. I mean, that seems kind of silly, doesn't it? You cannot do this without investment. So this goes back to the point, reaching a new level of connections, which is a new level of balance or homeostasis between these circuits, is hard. And it's hard unless you create an environment or a goal to do it. The brain needs to know you want to do that. And it only knows that when you're doing it. Sounds kind of a circular argument here, doesn't it? But that's the point. The point is, it's all about creating a new, stronger circuit. We call that adaptive. Homeostasis means a new sort of system that's working together. But to drive it, to break the old, to go to the new, that's where you're really kicking butt. Now, exercise happens to have kind of some of those qualities. I can make a goal to be a better tennis player, right? I can be a goal to be the best volleyball player in the world. Now, that's achieving pretty high, but you can do those goals. They don't have to be that high. That brain is happy, well, to learn a new tool. Maybe learning to play piano. It's happiest when it's been given an opportunity to do that. And so that gets to the next point. Plasticity fundamentally is encoding that experience. You see, you give it the experience, it encodes it, a new connection is made. Voila. Okay. And what's so fascinating about that, and this is the part that I think became an aha moment for me, absolutely, and how this whole thing comes back to exercise and Parkinson's disease, is that not only does practice, goal setting, learning something new, a new experience, right, drive this circuit to a different level of connections, but it can also repair or restore behaviors. Do you understand? If I have a lost behavior, let's say I can't move a limb very well, right, because of circuit problem, maybe an injury, I can, to some degree, recover that because of this, because of the same thing I'm talking about, because I'm experiencing something hard, something challenging. I can do what? I can go into that circuit and I can start making it stronger. Does that make sense? And hence that restores behavior. That's why we're talking about this. This is why this language even came in to the field of plasticity. You understand? This is why this all starts coming together. Not only is it how I learn, but I can apply it in the context of injury. And what do we call that, by the way? Rehab, right? Isn't that what we call that? Rehabilitation. Okay. So it's a mechanism to relearn behaviors. Now, there have been a lot of people in the field who've studied this, and I'm only showing you really a few points. Again, big picture. What do we know about plasticity? And I'm going to put it in the context of exercise, but you literally can substitute that idea for exercise with what? Learning. Learning, right? Learning. This is how connections are formed. That's how you make a new circuit, right? That's how these circuits change. They adapt because you're learning, you're creating a new goal. So Parkinson's disease and exercise, I could very well put learning down there. Okay. So anybody that's a teacher here, right, would know this. You can pick up any book on learning and you would see these same things come up. What's the first thing you need to do? Intensity. People define that in a lot of different ways. Some people say challenge, right? You make it hard, right? Sometimes we use that term in terms of practice, repetition. So intensity means a lot of different things. It's a very, again, when you're reading intensity, you have to think about what they're talking about, because oftentimes what you'll find is, the heart field wants you to talk about it in terms of heart rate. Yeah, I'm not talking about that. Okay. I'm a brain person. I don't really care about your heart. Just kidding. I have preference to your brain. So this is not a heart lecture at all, right? You're in the wrong room. We're talking about the brain. And when it comes to the brain, intensity means what? Challenge. Not easy. If I know Spanish, Spanish 1, all right, I'm not going to get better by going back into Spanish 1. I need to go to Spanish 2, right? So it is the idea of challenge, right? And repetition. The other thing about it is specificity. And what's interesting about that is it's kind of like about in the nuts and bolts of that practice. So, you're not going to do like a, part job. I'm going to kind of just try this out and see how I do. Again, for teachers in the room, yeah, you have a student that might go into your class, right? And they're kind of doing the basic stuff they have to do, but they're really not doing the reading assignments. They're really not doing a really good paragraph, in terms of writing, right? They do kind of a bad job, but they get by, right? Specificity is sort of about that. It's all in the details. It's all about what I'm doing, right? To really nail that, right? To really get good at that. And then comes the idea of task difficulty, which is the challenge idea, right? And finally, complexity. So what does complexity mean? It means that it's okay that you're learning a couple different things at the same time. And the best example that I can give you is some studies that have been done with throwing a ball. Okay. So if I'm learning to throw or catch a ball, let's say catch a ball, there's a couple of studies that have looked at, okay, well, let's compare two type of examples of learning to catch a ball, right? One could be that I take a certain distance and I stay at that distance and I keep, the distance doesn't change. The person's throwing the ball. It's the same, whatever, 10 meters or whatever. And then as soon as I get good at that, I make it 20 meters, right? And then I do that. And then I make it, 18 meters. You follow me? And if I compare that type of practice to someone who's learning to catch a ball that starts with 10 and then goes to 18 and then goes to 7 and then goes to 6, do you understand? It's really getting much more varied, much more complex. And then I ask the question the next day. I watch the kids the next day and see who's best at catching a ball. Guess who does better? The varied, you see. The varied. Complex is actually important. If you want to get good at something, you want to make it complex. Again, I give an example of a wide receiver or something. A wide receiver could learn to catch a ball if he goes 10 meters, 5 meters, 8 meters, right? Or he can learn to do it by playing a game. And it turns out that when you're learning to do it in the context of a complex environment, you're going to do better. So the idea here is messy is good. The brain loves it when it has to really needle down onto the specifics. Okay. This is to show you, and it actually happens to be a work that's been done in the cerebellum. This is a really old paper. Forget how old this is. It's like in the 70s, I believe. Anyway, all I'm showing you here is a rat to the right. And this little rat, the study here was to put these rats in very complex environments. And then the other set of rats that I'm not showing you here is on a running wheel. So all they're doing is they're in a little home cage. They have access to the running wheel and they'll run, 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 right? And the other guy's going, what the heck is this? Let me explore. I will now go over this board and then I'll go over these little ropes, right? And when I'm showing you to the left, the first arrow in C, I apologize, yellow, I will never use yellow again. It's not showing up well. The first arrow to the left, see this, C? AC is this guy on this little tightrope, got it? And this column is way bigger than all these other columns, okay? This column represents connections, okay? So his little connections, and it happens to be in the cerebellum, one of my favorite areas, is way more than all these other little guys over here. And guess what those other little guys are doing? They're on their little exercise bikes. They're just worried about getting their heart rate up, okay? So to remind ourselves, getting your heart rate up is not what this is about, okay? Getting your heart rate up may help your heart and maybe get blood flow up. And like I said, I don't knock blood flow. I mean, I like blood to my brain. But if you want to make a change to a circuit, that ain't going to happen by blood flow alone. So it's showing you that connections are everything when it comes to this little guy trying to figure everything out. Now, when you look to the right here on the D, okay, look at FX and VX, these two guys in the middle, particularly the one here in the dark gray, that's a person on a real hard exercise bike. Their heart, that what it says is blood flow. That's angiogenesis, that's blood flow, lots and lots of blood flow, but it's not connections. That's what I'm saying. Okay, good enough. So we do a lot of work with animals. This is just a very expensive, way too expensive treadmill. And this is how we do it. We literally, these are Parkinsonian animals that are put on the treadmill. This is very old data. This is some of the first data that ever showed what was happening in the brain in the context of exercise. And I will promise you that these mice are working hard, very hard on this. First of all, it's not a natural state for animals to be running like this. You probably haven't noticed. Not a lot of treadmills in the New York subways. And they're learning to stay up in the front of the treadmill. But more importantly, this is just showing you the difference. And again, this is very old slide showing you the difference. These are both Parkinsonian animals. The one at the top has been doing a lot of running most of his life. And the other guy, also Parkinsonian, is the couch potato. And the behavioral outcome here is obvious. Now, when I was starting this off, when we were starting this off, this was not known, actually. This is crazy, I know, because it seems so intuitive, but this was not known. And so we were showing like, they're moving better, right? But what came out of this was trying to understand, what was causing it. And the first thing, I'm going to move on really quickly here, I wanted to show, and I don't think it's emphasized enough, is that when we looked at dopamine levels between those two animals, what you see in red are two different groups of animals. To the left, this column to the left is the non-exercise, and to the right is exercise. One of the things I want you to see, look at that, they're even, right? Even. So we've never said that exercise increases dopamine levels in the brain. I've never said that ever, because we don't have that data. Nobody does, because it doesn't happen. Exercise does not cause neurogenesis. It does not cause new cells. And anybody who says that is wrong, just blatantly wrong. We've looked everywhere, and it's not about new cells, and it's not about making more dopamine. What it is, though, about, and this is a very fancy study that we did way back in 2007. All this slide is trying to show us to the right is when I look, and this is a part of brain, so it's kind of a crummy little picture of a piece of brain that's been laid out flat. It has numbers in it because that's where we poked a needle to see how well we can record how much dopamine is being released. Not the amount now, but how much of dopamine is being released, how fast it's being released from the dopamine cells and from the dopamine terminals. And what I can tell you in these areas is that dopamine is being released very fast. So what does that mean? It means that while exercise is not changing necessarily the amount of dopamine, what it does is it makes it more available. And that was the point we've been trying to make clear for a long time. It makes dopamine super efficient because it's certainly not being stored or being left to store in the dopamine. It's being utilized. And why would that be? Oh, I don't know. I'm trying to make a new connection, guys, right? I need some help here. While connections is all about practice and repetition, what did I tell you was the role of dopamine? It's a super glue. It's the super glue. As these connections are being made, I need dopamine there to do what? To glue it together. So dopamine needs to be made available. It needs to be released. And simply doing exercise can absolutely do that. It can make it more available, but we can make it even more interesting. I'm going to jump around. What we wanted to do was look at the dopamine receptor itself. So the dopamine receptor is really important in Parkinson's disease. When dopamine is released in the basal ganglia, I'll explain this slide in a second. When dopamine is released and working on a connection, it has to have a receptor to work on. And that receptor is called the D2 receptor. We can image it. So we image it with an animal and actually a human. We're not taking the brain out now. We're actually using an image that lets us look inside the brain to look at changes in the dopamine receptor itself. I've already showed you that exercise increases the release of dopamine, and that's a good thing. But what I want to show you here, this is just one of the first studies that we've done. We've done, and other people have actually repeated this study now, but we were the first to show this, which is, look to the left. This is a saline. This is a normal, I was going to say human. No, it's not a human. That's an animal brain, sorry. In red is the dopamine receptors. In the middle is what happens when you have dopamine depletion. The dopamine receptors go away, and this is exercise. So we see an increase in dopamine receptor level in the brain. Now, you're thinking, well, why do I care about that? Well, because what I want to say is while dopamine is not increasing overall, what exercise is doing is changing the handling of it. Not only changing the handling of it, but it's also changing where the target is. The target where I need it to work on these connections is going way up. And that's what you're seeing in red. And we were able to replicate this in humans. And all I want to show you, just ignore to the right. Again, we can do that looking at a brain MRI. This is a really unique type of way of imaging the brain. 1A across your brain doesn't look blue like that. Just don't, yeah, it's not. It would be cool if it was blue, but it's not blue. This is all from the special imaging, and red is the dopamine receptors. All I'm going to show you is we can totally image that. And what we're able to show in 1C, this is a person who's exercising. We can see that it's increased, is what I want to say, in people with the exercise. So not only were we able to say that, let me go on. Not only were we able to say that, okay, these animals look better, but the cause of it is related to connections through dopamine availability. Dopamine is doing its job. It's making itself more available to help these connections come together. Okay, so let's look at the connections, our favorite topic, and yet we haven't talked about it. So let's talk about that. So you remember this picture that I showed you. And again, I'm showing you some cells here. Again, you can't see that on an MRI. You can't even see that with taking the brain out. You need a microscope. But what we can do is we can fill these cells. And it turns out that these cells are in that part of the brain called the basal ganglia. Remember, the basal ganglia is where I said dopamine is dropping off there for motor movement. Basal ganglia is one of the key structures for movement. It's not the only structure, because remember, things are always connected up. In fact, the basal ganglia is also connected with the cerebellum, and it's also connected with the prefrontal cortex. But we're going to pick an area to start because the basal ganglia is a key area. Think of it as the engine of the car. And so we filled these cells, and again, we are looking to see, all right, we fill the cells, we see all these wonderful little connections in a healthy basal ganglia. And then again, which I pointed out, as I deplete dopamine, not having dopamine around, the connections start kind of fraying. They fall apart a little bit. Now, you shouldn't be surprised by that, right? Because I told you, as connections are made, right, I need the superglue around. I need it around to connect up. So it's not surprising to say, well, okay, but what happens if dopamine levels are down? What happens to those connections? And the bottom line is, well, they're not happy. They fray a little bit. And I'm just showing you an example down below, bottom right, that little thin white line there is showing you where all these little connections should happen, these little white dots. They look like thorns, but this is where the connections are. I'm not showing you the full connection. I'm just showing you part of where the connection would attach. But I'm showing you that they change. They get diminished. So we decided that same animal that I'm talking about, we saw dopamine. Okay, the next question, okay, what happens to these connections? I'd like to know that, right? And all I'm showing you is what took a hell of a lot of time. And this is why, PhD programs, not to get off the track so much, but researchers, PhDs, is the backbone of this country. If we don't have PhD programs, we're all in big trouble. And well, I have to tell you, we're in trouble right now. PhD programs are shutting down because of loss of money right now. That's a whole nother topic. But anyway, just thought I should share that. And if you look to the right here, I'm just showing you 3 different examples from 3 different brains, all right? I'm just showing you on one slide just for convenience so you can see directly in your, you can visualize this. This is what you can see. Watch. Sailing is a normal animal. Here's a dopamine depleted animal. They do not even look similar, not even close. And here's the exercise. All right. That's time in, guys. That's an investment. And that isn't going to happen by just giving dopamine. Do you understand? So that's what practice does. And when we looked at connections in those areas, so remember those little lines? Here's some pictures of these lines. This is normal in C, top C, sailing. Sailing plus exercise is just that. It's a normal animal with exercise. MPTP stands for Parkinson's animals, and MPTP exercise. What I want to show you, look to the right, bottom right, MPTP exercise. Whoa, right? Those are connections. Now, how much time do we have? 41. I'm obviously have a lot of different things to talk about, but I think what I'm going to talk about next is just what supplies these connections. And yes, I'm a proud mom of a USC runner here. He's now getting his PhD in molecular biology, and wish him luck. He's applying for postdocs. Okay, so what supports these connections? And one of the things that supports these connections is this wonderful green cell right here called astrocytes. Absolutely don't get enough credit. Astrocytes, these green structures, lie right next to neurons. They're kind of like the gas station of the brain. They are the energy supporter of the brain, right? Call them the electric cars now, right? Because we're not using gas anymore. It's all electric. So call it the electricity of the brain. And it's very unique because it can sense when neurons and synapses are working hard. And that's a good thing, because if that's happening, it needs to be supported by energy, right? Okay. So, and this is just trying to show you, this is an energy producing cell, astrocytes, right? And they deliver energy to these connections. And one of these energy molecules is called lactate, by the way. It's a type of metabolite. It's a metabolite that you can actually generate with running. It can build up in your muscles, but your brain can make it as well. And also when you run, that lactate that comes from your muscle can actually make it into your brain to those very areas that I'm about to talk about. And what I want to show you here is people have looked at this with exercise. Here's before you exercise, and all it's trying to show is how quickly lactate levels climb in the blood and then normalize. So we had a student in the lab who was very interested in this question. And all I want to show you is we're showing you, if you see these little kind of what look like little spider web things, these are actually astrocytes. And we're looking at, in the bottom here is the basal ganglia, and the top is the thinking part of the brain. And all I want to show you is they get much more complex. We were able to show that astrocytes, just like connections, over weeks. So it's not immediate. Remember, it's time. Remember, if we've learned anything, you need to invest in this. It's not going to happen overnight. You need to keep practicing. But the point is they do get nice and rich. And that's a good thing. Finally, okay. I'm going to end because I know we're running out of time really quickly here. I want to end with just one other point about the types of exercise. I think you've kind of come across, from everything I'm saying, you're going, wait a minute, plasticity, connections, oh, right, it's learning. And we're substituting that for exercise, okay? Now, I use the term skill because to me, it's the easiest way for me to say it's not just any exercise, it's a skill exercise. And the reason I use that term is on purpose, because people can think of exercise as just, riding your bike, getting your heart rate up, right? I'm using that skill because I'm trying to say it's all in the detail. It's not just about moving your arms and limbs about, right? That's why I use that term. I want to drive home the point that this isn't just any exercise. This is a very, very particular, very detailed, very complex type of practice. And then we have what's called aerobic exercise. And I asked, people say, okay, well, does it matter what I do? And I think I showed you something, at least from the cerebellar data, right? That wasn't quite exercise. It was just a rat moving in a complex environment versus a wheel. But I can address that question. And this question, actually, I should say, was addressed by a very good colleague of mine, also a good collaborator. And he kind of tried to address this question with putting rats, and these are Parkinson's rats, on a skilled exercise versus a simple wheel. Now, one of the things you're going to see is that is not an easy wheel to run on, right? Because there's holes. That's hard. I'd call that skilled, wouldn't you? Yeah, that's hard. That's complex. I like it. And what you see over here is kind of a plastic wrap over those things. All right, that's not hard. Now, what you do is you match those two things for speed. Now, I'm not going to start off fast. Are you kidding me? I'm going to kill that poor rat if I do it fast. So I'm going to build it up, right? I'm going to keep doing it harder, 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 harder. You get the picture? It's complex, it's challenging, and it gets harder and harder. So over 4 weeks, okay, this animal on that skilled exercise is kicking butt. And he's been working real hard to do that to match the other animal that's just been on the smooth wheel. But what I want to show you is something that is super duper cool. You can look after these animals exercise. I can actually look where the blood is going. And we can do that by tagging the blood and asking a very simple question. Okay, where's all my blood going? And what I really want to point out is the difference between these two brains on the left versus these two brains on the right. Red is blood flow, guys. Red is blood flow. Now, you can say, well, if it's just exercise, blood flow is blood flow, right? No. So why would these two things look so different? Why? What is causing that? Why would blood look different in where it's going to the brain? This is prefrontal, is the thinking part of the brain. And here we have the motor cortex that's affecting thinking and movement. I'm telling you, The only difference between this is skill. They're matched for speed. Whoa, what does that mean? That means the brain has full control over this. That means what I do, the goals that I set, the circuits that I affect by doing very specific tasks, by getting engaged in that, the neurons, the connections, the actual activity is telling the blood, get your butt over here and support this activity. I need energy. I need that energy here. All right. The brain is calling the shots. It's not the heart. It's not the blood flow. It's the brain. Why do I care? Because it goes back to a very, very fundamental idea. If I want to change my brain, I better damn well do something about it, but it's not going to happen if I'm not what? Engaged. If I'm not committed, if I'm not engaged, if I'm not trying to learn, if I'm not trying to make it complex, if I'm not trying to make an investment. That investment is everything. And I think I'm going to end it right there. Boom, 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 boom. Sorry, lots of stuff. Bop, bop, bop. There you go. Summer Olympics 2028. We hope. We'll see. Thank you.
Thank you so much, Dr. Petzinger. So I don't know. I think we could have listened to you for a little bit longer because this is so fascinating. But we do have some questions related to that complexity. So people are wanting to know if you can give example of a skill-based exercise versus just an aerobic exercise. We can figure that out. But what do you mean exactly in terms of a skill-based exercise that people would be doing?
Yeah, absolutely. Well, I'm going to answer that in two ways. First and foremost, if anybody knows anybody in the physical therapy field, and I have a lot of friends in physical therapy, one of the things you learn really quickly is that it's actually kind of impossible not to do anything without some level of skill, right? I mean, the nature of our movement, right? So I would argue, the truth is there isn't anything purely aerobic unless you've got someone literally with their hand on my heart squeezing it, right? I mean, the bottom line is everything has some level of skill. So obviously I can make things more skillful. I can dial that up. I mean, I can do like tennis, I don't know, pickleball. I think that's really popular right now, right? I can do any type of motor movement that's new to me or something I'm getting better at, right? That is what skill means. I'm just moving in a more complex way. And, I think that, anybody, that watches sports or really, any type of activity you can imagine, even, in grade school, it requires some skill. So the question is, does walking require skill? Well, it depends on what you're doing. Maybe if you make it in a new environment, like let's say you're walking now on a trail, right? Where you're having to be a little bit more engaged with what you're doing, if that makes sense. So you can always ratchet it up by, either changing up the environment or, walking in different contexts. Anybody that goes to the beach, you try walking on sand or running on sand, that's hard, right? So you can always make even the things that you're routinely doing a little harder. I'm not big on saying I'm walking and then say, oh, I'm walking and I'm walking my dog. I'm going, yeah, no, you're walking your dog. I think that for this sort of investment, I appreciate the dog needs a walk, but I would argue you still need to put the investment in. And yeah, does that answer your question?
Does, but I'll take it like a next step. So we've heard like you should be exercising for maximum benefit at least 80% maximum heart rate. How does that jive with
Exactly.
Yes.
Exactly. That's exactly what I'm talking about. Yeah.
Yes.
It's very confusing. And I have to tell you, the brain field got usurped by those darn heart people who love to talk about heart rate, right? And it's certainly easier to say. And I'm not saying that your heart, I'm the last person to say I don't need my heart, okay? And obviously getting good flow to the brain is good, and there's certainly benefits for that. But when it comes to learning, right? Think about learning again. I think that's the best way to start with. You're not going to learn if you don't make things harder and you don't challenge yourself. But that doesn't mean I need to get my heart rate up necessarily. I give an example, and I'm probably going to not be correct when I say this, yoga. I mean, you're probably getting your heart rate a little bit up with yoga too, but that's very skillful. And that's not getting your heart rate up. So I think when we talk about learning, and again, if there's teachers in the crowd, they can certainly appreciate this. It's about investment in time, and it's repetition and practice. Now, intensity, again, usurped by the heart people. I mean, their language is easier to understand. Oh, I get my heart rate up. I get it. But as I pointed out, that's different than learning, where you're having to make things complex and skillful, and you're trying to figure it out, and you figure it out because you're doing it a lot and you're getting better at something. What we say is 3 times a week, because that's where the studies are. And 3 times a week is probably reasonable. And if you do something 3 times a week, you're going to get better at it, right? If I'm getting better, that's a good indicator. And you don't want to be doing the same thing over and over again. And I'm going to emphasize again, it doesn't really matter what you do, because it's called the brain. Like, the brain doesn't know, right? It can't say, oh, it's this. No, it just knows what you're going through to get the new goal. Does that make sense? Now, I think that everything we know about the brain in terms of connections is true. Everything I said, it's about learning, complexity, and I would argue the kernel, like the fundamental idea of that, if you really wanted to bring it on home, is called problem solving. Really, it's solving a problem. When you solve a problem, it's actually what creates the connection. But think about everything you do to solve the problem. I mean, you're kind of thinking about it different ways. You're kind of repeating it again. You may be practicing it again, right? I say those things because they're truths about how the brain works. We're just trying to think, oh no, now I need to apply it to an exercise, but it doesn't change, really. The rules really don't change. They're that broad. And I like that. Why? Because it makes things simpler. It doesn't matter what you do as long as I'm using those parameters. It's hard. I'm not repeating the same thing over and over again. I might mix it up a little bit, do it in a different environment. Maybe I now use my left hand instead. You see what I'm saying? So it's really practice, complexity, all those things that make you good at what? A language, math, right? A pianist, it's those sorts of things. Yeah. Someone had a question?
Yeah, we have a question. Is rocksteady boxing such a skill-based exercise?
You guys tell me. Tell me, what do you think? What are you doing during rocksteady boxing that you think would be complex? Sequencing, right? You're having right, left, right. How you're moving your arm, how you're balancing in the context of that, right? Yeah, of course. It's not just, oh yeah, no, my heart is. No, I mean, if it was just that, I might as well just get on a bike and read a newspaper, right? So boxing, of course, it's complex. And what makes it complex is when you're achieving a new level of expertise. Do you see what I'm saying? It's that you're getting better at something because you're putting the investment in. And again, I'm not knocking the heart people. God bless them, right? Your hearts are important. I'm just trying to tell you something. I'm trying to give you kind of a fundamental rule of life. I use exercise because I'm interested in that. Tennis, of course. Who said that? Yeah. I mean, come on, guys. You've seen these tennis players, right? I mean, like, you can get out there and learn to play like that, right? You've got to practice. Of course that is. But my point is, this is always true. These are truths. And I like that because it makes it very accessible. I get it. I understand what this means. It's not like, oh, it's about the bike. It's about this. It's about, and not that I don't appreciate what everyone does to develop great types of exercises, make them fun. And we know why that's important, because I'm likely to do it, right? When you're working your butt off, you'd like it to be fun, right? So those things I'm not taking away from, but I also don't want to lose the forest through the trees. Okay. This isn't magic. This is truths. This is the same thing that happens. I don't care whatever you learn. It just so happens that when you're doing physical movement, it's a biggie. If we had to talk about anything about what the brain's purpose is, really, it is about, well, I could even say use of tools, right? Cavemen, that's how the brain evolved. It was use of sequence of movements. That's fundamentally how the brain evolved. And from that came language, because language is about sequence. And from that became really evolve thinking. I mean, thinking is just like whatever. Yeah, okay, now I can think, whatever. But the point is, it's really fundamentally about moving and learning to move in sequences that are complex and novel. And the brain loves it. It needs that goal. It wants that goal. And there is nothing, and I mean nothing, that you could ever imagine you could make that's going to replicate that. There is no exercise drug. I'm sorry, you'd have to rebuild the brain. I hate to break that news, but there are so many things that are so unique to the brain that have to do with how I learn, practice, repetition, and those circuits. Good luck, right? Now we can use and identify therapeutics to make it better, to enhance it, but nothing is going to replicate the brain, because that's essentially what you would have to do. Yeah, that's huge. And I'm not into tackling things that are pretty much not even possible, right? Okay, maybe with robots, but not with our brain. So it makes more sense to understand the rules of the game, the systems that are involved, how I can enhance this effect, right? What's causing the blood to go there? What aspects of neural activity is telling the blood, get your butt over here? I mean, that would be kind of cool to know, right? Maybe I could, with a therapeutic, make that even better, right? So it's about not replacing it. It's about making it better, right? It's about making it stronger. I call it visually like riding the wave. I now understand how a wave works. I'm going to make that wave stronger yet. You follow me? We're not fighting the system. We're working with the system.
So last question is, how long do exercise-induced improvements last?
Well, how long does learning last? Right? It's the same mechanism. I'm telling you, it's the general rules. Okay, let's start with Spanish. Okay, everyone's been in a Spanish class. Am I right? I think so, or French or whatever. Everyone's been in a language class. You take a language class, and let's make it high school to make it a little bit, oh no, college. Okay, make it a little bit more sophisticated. You're talking maybe some basic language. You're kind of proud of yourself. You're now talking to your friends a little bit. And then the next semester, you go abroad, right? And you're going, uh-oh, right? Everything I learned, I kind of know that, but now I'm here practicing again. So it's like learning. There is some carryover, but the more you invest, repetition, and the more ways that you use it, what's going to happen? It's going to last longer, right? It's going to be more embedded. I swear to God, this is the brain. There's nothing magic about this. The same rules of learning apply with physical movement. Yes, I'll get some benefit in the short term, but if I don't use it, right? If, like my language, if I'm not using it regularly, okay, I'll have some, but I won't have it as good, right? And that's normal. And then the elephant in the room, of course, is aging itself, right? As we age, we know that the brain, in terms of energy, is maybe not as efficient. So when I practice, maybe it takes me a little longer to do some of these things. Frankly, I think a lot of us should just move into the aging field, because really that's going to be the limitation at the end of the day. But yeah, so if, when you ask about questions like, okay, how long is exercise, lasting, I would go, okay, think about language. That's a good example. You need to keep using it. You need to keep doing it. That's the way the brain works.
Awesome. Well, I want to thank you. I appreciate this. We probably could go on for another hour, but I know that we have to end the program for the day. You've given us a lot of your time and your expertise. And real quick, everyone, we are going to pop up those 2 poll questions. If you would just take a minute and answer those. And in the meantime, I want to thank you so much, Dr. Petzinger. And of course, I want to thank CND Life Sciences, who are our partners in this program today. We're so thankful to have experts like Dr. Petzinger and the opportunity to really dive into some of these brain health.
Okay.
So I'll give
Thank
you guys a
guys.
second.
Yeah, wish me luck on my grant. We're moving to foundations, as you guys probably know. So these foundations are getting hit hard right now. So keep good thoughts for research, guys. We're going to need it. Okay, take care.
Thank you.
Bye-bye.
All right. Well, we are thankful if you have filled out the poll results. We appreciate your time. We hope that you enjoyed this. There will be a recording on our Proactive Brain Health Alliance website. We've dropped the link in the chat. If you want to save your chat, you can grab that link. If you've not had the opportunity to view our website yet, we invite you to do so. And we thank you everyone for joining us today, and have a good day. See you.